Yeah, dear participants, so welcome back to our online certification course on analog electronic circuit. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion, it is feedback. It is rather continuation of feedback system, and specifically we are going to talk about application of feedback circuit in amplifier. So, the amplifier may have transistor level circuit as well as op amp based circuit. According to our overall flow, we are in week 10 and we are in module 9, and we have discussed about basic 4 configurations, feedback configurations and their characteristic. We also have discussed about effect of feedback on frequency response of an amplifier, and today's discussion, it is more like continuation of the basic 4 configurations, and specifically how those configurations can be deployed on practical circuits. The practical circuit can be either transistor level. The examples we will be talking about is primarily BJT, and then also we will be talking about deployment of feedback system on op amp circuit. So, we can say that we are at module levels as well as at subsystem levels. So, the concepts we are planning to cover today, it is listed here. So, we shall see how we can deploy or how do we decide different feedback configuration in BJT circuits, BJT amplifiers, and there we will be talking about specifically 3 different configurations, which will be giving us fair idea how to deploy the feedback configuration. These are the 3 possible configurations we are talking about. Of course, one more configuration it is skipped due to the shortage of time. So, we will be talking about voltage sampling and shunt feedback, referred as shunt feedback, and then current sampling and series mixing, referred as series feedback, and then the third one, it is voltage series feedback or shunt series feedback. And then we shall also talk about a little bit extension of the basic feedback models, which we need to discuss before we go into the feedback circuit using op amp. And for feedback configuration around op amp, we do have different possible examples, namely inverting amplifier, then integrator and differentiator, and then non-inverting amplifier, and then also we can discuss about a circuit which is having 2 feedback loops. So, these are the enlisted items we do have for this lecture. So, to start with, let us summarize whatever the things we have discussed in our basic 4 configurations. So, yeah, so here we have 4 different configurations. So, the name of those configurations are given here, namely voltage shunt, current shunt, voltage series and current series, or you may say shunt, series shunt, and then shunt series and series. So, you may recall that depending on these configurations, we also can say what type of signals we do have at the input, and also we can see what type of signals we do have at the output of the system. Here we do have the basic model of the feedback system, negative feedback system. The input, either we may call this is the primary input, or just by observing this input we can tell that what kind of amplifier we do have, or rather the input type and the output signal type, it will decide what kind of amplifier we do have. And that also decides that what kind of feedback we do have or feedback network we do have. Say for example, if we consider the first one, it is the signal here, it is current, and signal here it is voltage. So, the amplifier, the forward amplifier, it is essentially trans impedance amplifier, or we can say that A is Zm. So, then of course, we know that once we are deploying the negative feedback system, according to this formula, the forward amplifier gain A, it is getting reduced by this factor, which is referred as desensitizing factor 1 plus beta into A, where this beta is the feedback factor here, and A, depending on the type of signal, it may vary from Zm, then AI, the current gain, voltage gain, and transconductance, Gm. So, whatever the configuration we do consider, essentially this is the formula by which we can say that A, it is getting reduced. So, the arrow we are putting here indicating that the feedback effect of the negative feedback, it is reducing this A by a factor, desensitization factor of the circuit. So, if I on the other hand, if I consider say this configuration, then the input is current, output is also current, and A is current gain, and once we have the proper feedback connection, we are expecting that this current gain, it will get reduced. So, likewise, if we consider the third configuration, the voltage gain, it will be getting reduced. Likewise, the fourth one, transconductance, it will be getting reduced. So, whatever the configuration we do have, if based on that configuration, once we know that what is A, and then we can say the corresponding A, it is getting reduced by this factor. And the factor here, what is the basic purpose of reducing this this A? What you can say that if I assume that beta into A, it is much higher than 1, then we can approximate this AF feedback system gain, AF is equal to beta, which means that the system transfer function or primary input to primary output, it can be decided by the feedback network. So, if we want to stabilize the specific parameter, say Zm, then we should be selecting the first configuration. On the other hand, if we say want to stabilize say voltage gain. So, if we want to stabilize the voltage gain, then we should be selecting the corresponding configuration here. So, then we can say that AV, the corresponding AV of the feedback system, if I call AVF. So, this AVF, it is getting converted into AV divided by 1 plus the corresponding beta into AV. And again, if I consider this is much higher than 1, so this can be well approximated by 1 by beta. So, the basic objective of having this negative feedback system, it is to stabilize this A, whether it is Zm, AI, AV or Gm, and it should be stabilized to a value which is defined by the feedback network, which can be decided by a designer based on the requirement. So, for every configuration, while A is getting reduced, the resistance, input resistance and output resistance on the other hand, they may have different changes. Say for example, if I consider shunt configuration, then input resistance it is expected to decrease by the same desensitization factor, and also the output resistance it is getting decreased by the same factor. So, while we are trying to stabilize this Zm, we should be aware that the corresponding input and output resistance, they are also getting decreased. So, there may be different objective to follow this configuration or to get this configuration. One of them, it is of course to stabilize the Zm. The other objective, on the other hand, it can be reducing the input resistance and or reducing the output resistance. So, this combination, however, this combination is fixed, reducing Zm and then reducing R in and R out, it is fixed. And if we are very sure that we are looking for this characteristic, then we can add the negative feedback system in this shunt configuration. And so, likewise, if you are very clear that which parameter you like to stabilize, namely defined by the parameter of the feedback network, based on that you can select the corresponding circuit configuration, and also you should be aware that what may be its corresponding consequences. And the consequences, as I said, that for this case both R in and R out, they are getting reduced. On the other hand, for the second case, the R in, it is getting reduced, but then R out, it is getting increased. So, likewise, if I consider the third case, excuse me, likewise, if I consider the third case, we do have the third case here, and for this third case, the input resistance, it is getting increased, and output resistance, on the other hand, it is getting decreased. So, likewise, the final one, for series configuration, feedback configuration, both R in and R out, they are getting increased. So, this table, this summary, it is very handy, and this will be helping us to decide which configuration we are looking for to achieve some requirement, namely to change the input and or output resistance, or probably either current gain, voltage gain, transimpedance or transconductance we like to stabilize, defined by the feedback network. And while we do have the it is having different possibilities, the corresponding feedback factor beta FB, we are calling this beta as beta FB to avoid confusion with the beta of BJT transistor. So, if it is say Zm, the unit of beta FB it is mho, and on the other hand, if the A it is transconductance, the unit of beta F it is ohm, and on the other hand, if A is either current gain or voltage gain, then beta FB it is unitless. Okay. So, now we should also be aware that suppose if I decide one specific configuration and we know that the corresponding changes are happening, then we should also be aware that what will be its consequences, namely what will be the variations on the other parameter. So, in the next slide we are also having one important table along with this table, which tells us that what may be the corresponding consequences on the other parameter. So, here we do have the same table, which will be helping us to decide basic configuration, and then we do have the other table here, which it will be helping us to understand that what may be the consequences on the other parameter. So, say for instance, if I consider this configuration and I know that Zm got reduced by the desensitization factor like this one 1 plus beta into A or whatever you say beta Fb into A, and Rin also is getting reduced by the same factor, same thing for the R out. Now, suppose we like to know what may be the what kind of changes are happening on the other parameter, namely current gain, voltage gain or transconductance for this configuration. Then we need to know that how do we express those parameters in terms of this Zm and Rin and R out. Here we do have a table which is representing the other parameters, say current gain in terms of Zm and Rin and R out. So, if I see this this column, that gives an indication that the current gain of this circuit, this configuration, which is Zm divided by R out. So, we can say that this is indicating that current gain of the circuit E I is equal to Zm divided by R out. And this table suggests that both Zm as well as this R out, they are getting reduced by the same factor. So, we can say that this A I, the current gain, will not be having any change. So, we can say that it will be having no change. Now, we can also work out on the other parameter, say for example, if I consider the voltage gain, and the voltage gain its expression, it can be given by this factor multiplied by Zm. So, we can say that this Av equals to Zm divided by R in, and again both the Zm and R in are getting reduced by the same factor, desensitization factor, and as a result here also there will not be any change. So, I should say here also we do not have any change. On the other hand, if I consider say transconductance, so the conductance of the circuit under this configuration, we can say that it can be expressed by in terms of Zm and R in and R out by this, or we can say that transconductance of the circuit Gm equals to Zm divided by R in and R out in the denominator. And as this table suggests that both R in and R out are getting reduced by the same factor, and of course, Zm is also getting reduced, but since we in the denominator we do have two factors. So, we can say that the net effect here, the denominator is getting reduced, that means it is getting increased by the desensitization factor. So, I should say that by looking into by combining this table and combining this table, we can also see the changes in the other parameter by considering the corresponding parameter here. Now, let you consider other example. Say, let me clear it. Let you consider say the circuit in this configuration, voltage series or shunt series configuration, which indicates that AV it is getting stabilized or reduced by the desensitization factor. So, we can say that this A it is AV, and appropriately you have to see what is the corresponding beta. Of course, it will be unitless, and this is also AV, and which suggests that after having the negative feedback configuration, the system gain, voltage gain, it will be reduced by this factor. And while we are making this configuration, as this table also suggests that the input resistance is getting increased by the desensitization factor, and the output resistance on the other hand, it is getting decreased by that factor. So, we are clear that this configuration, it is having impact on voltage gain, input resistance and output resistance. So, we can say that AV we know for this configuration. Now, we like to know what will be its effect on the current gain. So, to look at the effect on the current gain, now we will see this column, which represents that the expression of all the parameters in terms of AV and input resistance and output resistance. So, if I see the current gain, which is AV times R in divided by R out. So, we can say this is equal to AV divided by R in and R out. Sorry, let me write here AI is equal to AV times R in divided by R out. And as this table suggests that AV it is getting reduced, R in on the other hand it is getting increased, and R out on the other hand it is getting decreased. So, in effect this AI it is getting increased by this factor, desensitization factor, because this decrease and this increase they are getting cancelled. We do have the denominator is getting reduced, and hence the net effect it is the AI it is getting increased. So, I should say that before we make the feedback connection, whatever AI we are having, that AI after making the feedback connection is getting increased by this desensitization factor. So, likewise if I consider say GM. So, if I consider GM here for this configuration, and the GM it is its expression in terms of AV it is given here. So, this is equal to AV divided by R out, and as this table suggests that both AV and R out are getting decreased, and hence this GM it is not having any change. So, GM remains unchanged. And then if you look into the trans impedance Zm. So, if you look into Zm, so Zm it is AV into R in, and this AV it is getting decreased and R in it is getting increased. So, again here also this Zm is not having any change. So, both Gm and Zm are not having any changes, but the AI it is getting increased and AV of course, it is getting decreased. So, like that you can look into the other configurations, namely series shunt and maybe series and you can see what kind of changes are happening in the main parameters and what kind of corresponding effect it is falling on the other parameters by looking into either the first column for the series shunt connection, or for series connection you can look into say third column to see what kind of changes are happening in other parameter. So, I think this summary table, it is very useful to deploy the feedback configuration and deciding what configuration you are looking for to achieve some objective, and also it is giving us the information about the changes or consequences on the other parameter. Now, let us look into more towards the actual circuit then. So, what we will be looking for, it is in fact, let me also summarize some other aspect, namely, so we do have this table, which gives us the information about how to select the configuration. After that, what you do? So, rather what may be the overall procedure to incorporate feedback loop in an amplifier. So, here we do have the list of the activities we have to do. First thing is that we have to select the right circuit configuration, and also we need to be aware about the consequences, what are the changes are happening not only in input and output resistances, but also in other parameter such as transconductance or voltage gain and so on and so. And the third one is very important, that if we consider the practical application, and if you really want to make use of this feedback connection to create some effect, and if you really want to know what is the effect, and intuitively if you want to calculate what is the corresponding changes, then definitely we need to have fair understanding of a suitable range of the parameters, or rather feedback resistance or feedback network. So, here we do have some guidelines which helps us to make the loop really effective according to this formula. Also we can intuitively say that what kind of changes are happening. So, what are the guidelines we do have? First thing is that whenever we are considering say this feedback system model, we assume that in case if there is any load, the effect of the load, it has been considered in A, which means that we need to consider A dash instead of A, or at least we make sure that the effect of the external load, it has been taken care, if it is possible to do so. And then next important thing is that we need to find the meaningful feedback network, or rather feedback factor beta f b, so that the loading effect of this feedback network on A and loading effect of the mixer circuit on feedback network, you can say it is it can be ignorable, or we can say that this A double dash, it should be approximately equal to A dash. A dash is the load, external load affected gain, and also the beta f b dash should be approximately equal to beta f b. And if we follow this appropriate range of beta f b to satisfy these two conditions, then you can intuitively say that what kind of changes it is going to happen in the circuit. Now, in case if these two approximations are still not valid, then also the circuit it will be working, but whatever the simplified expression and whatever the equation it is giving us in intuition that what kind of changes it will happen, that may not be really effective, and there may be significant amount of deviation from the simplified theory. Apart from these two approximation, we also need to say that beta into A, or we can say that A dash into beta f b, if it is much higher than 1, then only we can say that this is approximately 1 by beta f b, and then only you can say that the feedback system characteristic, it is solely or predominantly defined by the feedback network's parameter. So, to achieve this property, namely the AF solely defined by the feedback network, we need to have meaningful selection of this beta f b, and then only whatever the changes we have summarized in this table, namely increase or decrease of the resistances defined by this desensitization factor, it is directly applicable. But of course, even if you are not satisfying these conditions, then also the R in and R out will increase or decrease according to this table for this different configuration. Only thing is that their increase and decrease may not be defined by this same desensitization factor. We have to consider the corresponding deviation to get the more accurate change in the input and output resistance, and also the change in A. So, for practical circuit, as I said, it is better to have a meaningful range of on this beta f. So, in the next slide, let me discuss about what is the guidelines to really get a range of beta f b, rather going little detail of whatever the guidelines we are discussing now. So, yeah. So, to make the loop really effective and intuitive, first thing is that let you consider the loading effect on A. So, we should say that instead of A, it is better to consider A dash after considering the external load effect. So, in case if you have external load R L, and if we consider that R L on the circuit, then we can get load affected A, and then we can proceed further, namely we can try to calculate what may be the A f in terms of this A dash divided by 1 plus beta f b and then A dash. Now, next thing is that we need to find the suitable range of the beta f b. Of course, based on the nature of A, beta f b it is complementary in nature. So, that this product it becomes unitless, rather you may say that loop gain minus of loop gain it becomes unitless, and that is once you know that what may be the nature of this beta f b, next thing is that what is the meaningful value of it. And to get that to get a suitable range, we do have two things to satisfy, as just now I was talking about. A double dash it is approximately A dash, and what is A double dash? It is the loading effect of the input resistance of the feedback network, say R in beta, if it is much higher than the R out of the amplifier, particularly for voltage sampling, then we can say that this A double dash it is approximately equal to A dash. So, if I ensure that this condition is getting satisfied, then you can say that loading effect of the feedback network on the forward amplifier, it can be ignored. So, pictorially you may say that suppose this is the amplifier and it is having R out, and suppose we are making a voltage sampling, which means it is a parallel connection, and we do have the input resistance of the feedback network, which is R in beta, and so this R in beta, if this R in beta it is much higher than this resistance, then you can say that the loading effect on the amplifier or this output voltage hardly changes, even if I consider this R in beta. So, this is specifically true for voltage sampling, and of course, for current sampling the condition it will be the other way. On the other hand, if I consider the input resistance of the amplifier R in, and then we do have say current mixing. So, if we have current mixing here, so this is shunt configuration, and then we do have R out of the feedback network beta. So, if I consider this shunt mixing or current mixing, then if we satisfy this condition, if I say that this R out beta it is much higher than this input resistance here, then you can say that the loading effect on the feedback network from the input resistance of the amplifier, it is ignorable, and hence if I satisfy this condition, then we can say that this beta f b dash it is approximately equal to beta f b. So, this is giving us a good range of, or it is helping us to define what may be the suitable value of R in of the feedback network R in beta and R out beta. And then also if you consider that this equation, if it is giving us the expression of AM sorry AF in terms of beta FB, to get this we want this part should be much higher than 1. So, we can say that A dash into beta FB it should be much higher than 1, and this gives us the beta FB it is much higher than 1 by A dash. So, these two condition here, along with this condition, it will be helping us to find what is the suitable range of the feedback network circuit components, and that will be helping us to get very effective feedback connection. I think this will be very clear once you consider one practical circuit. Probably I do have the practical circuit in the next slide. Yeah. So, here we do have one application circuit shown here, which is common emitter amplifier. So, we do have common emitter amplifier. In fact, this is fixed bias common emitter amplifier, and we will be talking about its feedback connection, and our main target it is that we want a stable Zm defined by the feedback network. So, this is our main objective, and then we will be discussing how to decide the configuration and then how to select the component value. But before that, let me take a short break and then I will come back. 2 minutes.